So a direct consequence of the theorem that we have just proved is the following corollary. So content on a semi-ring is also monotonic and subadditive. Well, the proof is quite easy. So the idea here is we use the previous theorem. So say you have a content nu on H, and in this way we construct the content mu on the semi-ring, since we have established before that a content on a semi-ring is monotonic and subadditive. This implies that mu, and hence the restriction, is also monotonic and subadditive. So in this case, monotonicity and subadditivity of mu is inherited from the extension mu. So that would be the proof of the corollary. The next theorem can serve as an alternative definition of a premeasure on a ring. So let us consider a ring R on X and a function mu on this ring to 0 up to infinity. Then mu is a premeasure if and only if mu is sigma subadditive content. So subadditive content. Okay. So let us look at the proof for this direction. Okay, so sigma subadditivity of mu plus the fact that it is a content. Since we have a content on a ring, we know that the reverse sigma subadditivity is satisfied as long as the collection of sets is pairwise disjoint. Okay? And subadditivity and the reverse inequality for that would imply that our function mu would be sigma additive. So you have here one inequality, let's say, in this case you have the reverse inequality. Hence, the two terms would be equal. Okay. So that is the easy part. Now, for the reverse, so assuming that I have a premeasure, we only need to show that it is sigma subadditivity. We need to prove only subadditivity. Okay, so let us apply the definition or use the definition. So consider a sequence of elements where A naught is a subset of the union of A sub n and from 1 to infinity. Okay. So here we would construct a pairwise disjoint collection whose union is still the union of the A sub m's. We want that in order to apply the sigma additivity of the premeasure mu. Okay, so to have an intuition of the construction, let us draw the first three sets, say A1, A2, and then A3. So what we do here is to first say, let us set B1 to be A1. So let's say this is B1. The next set would be A2. Now I want this to be pairwise disjoint with respect to A1. So this would be a B2. In this case, this is A2 minus A1. And the next set, I want the next set to be disjoint with respect to the first two sets. So in this case, this would be B3. So we define B3 as A3 except the union of the two sets. And we continue for all n. So we'll let B1 to be A1. And for n greater or equal to 2, this would be an minus the union of the previous sets. Okay, now based on this construction, Bn is a subset of An. Since a ring is closed under set difference and finite unions, then this is a collection of elements in the ring. Furthermore, by construction, it is pairwise disjoint. And what is the union? The union would be the same as the A sub n's. Okay, take note that the B sub n's are obtained from the A sub n's, but then subtracting the previous ones. And you could easily see that here you still have the union A sub n's of the A sub n's. Okay. The good thing here is that the sets are now pairwise disjoint. Okay. Also, if you have the pairwise disjoint sets, B sub n's, since A naught is also in R, then this collection is also in R, and it is pairwise disjoint as before. Okay, and now if we take, let's say, the union of this collection, so let us apply the distributive law for sets. Okay, and take note that the union of the B sub n's, as we have said a while ago, is the same as the union of the A sub n's. This is the case since A naught is a subset of the union. So the intersection of the two sets would be the smaller set. In this case, it is A naught. Okay. So now let us take the value of A naught with respect to mu. Since mu is a pre-measure, it is sigma additive. So this is mu of Bn intersection A naught. Because in this part here, we need to, it is assumed that mu is a pre-measure. Okay. So in this case, I can estimate this. As the sum of the measures of the B sub n's, because one is a subset of the other, and a pre-measure is also a content. And since we have a ring, it is also monotonic. Applying monotonicity once more. Since B sub n is a subset of A sub n, then replacing the B sub n by the A sub n would lead to a possible larger sum. Again, applying the monotonicity. And here we could see that indeed mu is sigma additive. Okay, so that's an alternative characterization of a pre-measure on a ring. So according to this theorem, if you have a ring, then mu would be a pre-measure if and only if it is a sigma subadditive content. So you could replace sigma additivity by sigma subadditivity in this case, as long as the domain of the function mu is a ring. Okay, so for our next theorem, we would like to construct a content with respect to the product space. So suppose I have H and K, and these are, let's say, semirings on the set X and set Y, respectively. And I have two content spaces, the set X, the semiring H on X, and let's say mu. And the set Y, the semiring K on Y, and a content mu. Now, let us define the following function, the product of mu and nu. So this is now defined on the Cartesian product of the two semirings. And the definition, so the value of the cross product A and B is the product of the content of A with respect to mu and the content of B with respect to nu. So this is for A in the semiring H and for B in the semiring K. In this way, I perform the Cartesian product of the sets, the Cartesian product of the collection of sets, here the semirings H and K, and the product of mu and nu defined above. Then this is also a content space. Okay, so first recall that this is a summary on H cross Y. It's basically Hans' theorem that we have discussed in the previous lecture. Okay, so let us look at the proof. So for this theorem, it is enough to verify that this one here is a content. Okay, and we will establish this as follows. So suppose that I want to take the value of the empty set. The empty set is the Cartesian product of itself. And applying the definition, we have here the product of contents of the empty set with respect to mu and nu. And since mu and nu are contents, these two values are zero, hence the product is zero. Okay, so that's the first. Now let us establish additivity. So let us take a finite collection of elements in the product of semirings, H cross K, pairwise disjoint, having a union that is also in the product semiring. Okay, then this means that this is of the form A cross F for some E in the semiring H and for some F in the semiring K. Okay, so the Cartesian products A sub j cross B sub j's are pairwise disjoint. And if we combine them, it is also a Cartesian product of two sets, one in H, which we denoted by E, and the other one, F, which is in K. Take note that here, if you imagine, for example, the Cartesian products as rectangles, then we are telling here that the union of these rectangles, which are pairwise disjoint, is also a rectangle. Okay. However, there's no reason that the A sub j's are pairwise disjoint, also for the B sub j's. As an illustration, let us consider the following. So here, E would be the horizontal axis and F would be the vertical component. So E cross F would be a rectangle, and it is visualized in this figure. So on this example, N is equal to 5. This means that E cross F would be the union of these 5 smaller rectangles. If you look at the projections with respect to the first component, that is A sub 1, this would be A sub 1, this would be A sub 2, And same with a sub 3. This portion here would be a sub 5. And again, this portion would be a sub 4. Combining those projections, you will see that E is the union of the a sub j's, j from 1 to 5. And similarly, F would be the union of the b sub j's, j from 1 to 5. So for instance here, there's no reason that in general that the a sub j's would be pairwise disjoint. For instance, it is enough to consider these two rectangles here. The projections A2 and A3 are in fact the same. So the first components are not pairwise disjoint. And similarly for the b sub j's. So the idea here is that we construct smaller rectangles by, let's say, extending these lines. Doing that, we will generate smaller rectangles, which are subset of the others. Okay. And in this case, based on our example, we would have generated 9 smaller rectangles. And this would be C1, C2, and C3. This would now be D1, D2, and D3. And you could see, based on this, that your E can be written as the union of the C sub k's, k from 1 to 3, and F would be the union of the D sub l's, L from 1 to 3. Okay, here it is not necessary that the number of elements for the C sub k's and the D sub l's are the same. But in this example, they are the same. However, as I mentioned, it may be the number of rectangles may be different, or the projections would be different. The good thing here is that these are now pairwise disjoint unions. Okay. In fact, the general statement is valid. So we are claiming here that there exists pairwise disjoint collections, say C sub k. How many of them? Say n. Elements of H. And another pairwise disjoint collection. Call it D sub L. How many? Say P. Okay. Which are elements of K, such that E can be written as the union of the C sub k's, k from 1 to m, and F would be the union of the D sub l's, L from 1 to P. Okay, we already, or at least one can show that with respect to the original collection of Cartesian products, the sets involved in the first components, the union would be E, and for the second sets, the union would be F. Moreover, for each, say j from 1 to up to n, So this is the index corresponding to the original collection. There exists a collection of indices S sub j in S. And what is this S? Let us call this to be the index corresponding to E. And another subset called T sub j, which is a subset of T. This T corresponds to the indices associated with F, so that's 1 to P, wherein each A sub j and each B sub j can be written as follows. So the union of the C sub k's, K in the index set S sub j is A sub j, and the union of the D sub L's, L elements of the index set T sub j is also B sub j. Okay, so you just collect the indices. To have an intuition on what is happening in the construction, let us look at this part here and express A sub 1, A sub 2, A sub 3, A sub 4 as the union of the sets C. Okay. So you could notice that A1 here, C1, A2. In this case, this is the same as A3, and A3 would be the union of C2 and C3. So you just take the union of the first set involved. And then A4 would be C1 union C2. So that's C1. And then finally, A5 would be C3. And we could do this similarly for B. And I will leave the details to you. Well, you could see immediately here that B1 is C1, no, D3 and D2. And B2 would be D3, B3 would be D2, B4 and B5 would be D1. Okay, so going back with the general statement, this means that A sub j can be written as a union of sum of the C sub k's and the B sub j's as the union of sum of the D sub l's. Okay, accepting this fact at the moment, let us proceed with the proof of the theorem. Okay, also, you can show that the Cartesian product here is also pairwise disjoint, having the union S cross T. This comes from the fact that the A sub j's cross B sub j's is pairwise disjoint. Okay. Take note that if there are two elements in this, two common elements in this S sub j cross T sub j's, then that would imply a common element of the A j cross B sub j's, which is not possible. Okay, so we have formed a partition of the Cartesian product of indices S cross T. S cross T. Okay, so in principle, if we take the content of these 9 rectangles here, we should end with the content of the original, at least in this illustration, 5 rectangles. Let us verify that rigorously in the general setting. So let's start with the value of the union. So this the union of the original rectangles or Cartesian products A sub j, j from 1 to n. Okay, we could simply write this as mu times nu of E cross F, because we have denoted the union of these Cartesian products as E cross F. Now, the next step would be representing E as the union of the C sub k's and F as the union of the D sub L's. So this is the union of the B, or I should say C sub k, k from 1 to m, and then the Cartesian product of D sub L, L from 1 to P. Now, applying the definition of mu times nu, so this would be the product of the contents of the unions, respectively. The next step would be applying the additivity of mu and nu, since they are contents. And the C sub k's are pairwise disjoint. So writing that one, we have this product of sums. Okay, we could write this into a single sum, but now the indices come in pairs. Okay, so this is S cross T. If you recall, S here would be 1 to M, and T would be 1 to P. So you exhaust all possible pairs. Now, using the fact that Sj cross T sub j is pairwise disjoint and the union is S cross T, we can partition this sum as follows. So the sum j from 1 to n, and then the pair KL in Sj cross T sub j. We get all the terms because the union would be S cross T. And there's no repetition because the collection of indices would be pairwise disjoint. So indeed, we obtain the whole sum and there's no duplication. Okay. So writing this in terms of the following, So going back with double summation, and then applying the distributive property, we get the following sum. Okay. Since the C sub case, take note, are pairwise disjoint, you apply again the additivity of mu so that the second inner sum would be the mu of the union of the C sub k, k and Sj, and the second one would be applying the additivity of nu as well. This is nu of the union of the D sub L, L in T sub j. Okay. Now, going back above, I apply these two equations here, and you could recognize that this is indeed A sub j, and this is B sub j. So plugging that one, you end up with the following product. And going back to the definition of the Cartesian product of the two contents mu and nu, this would be this term. Okay, so that's a long computation, but let us summarize, or let us highlight the main part. So we started with the mu times nu of a pairwise disjoint union. We established that it is equal to the sum of the values corresponding to the Cartesian products AJ cross B sub j. And this proves additivity of mu times nu, and therefore the product, going back above, the product mu times nu is indeed a content. And this proves the theorem. Okay. Going back to the proof, we have used this portion here crucially, okay? But we have only established this using a particular illustration. Of course, this does not comprise for a formal proof of this remark. So let us prove this in a separate theorem. Okay, so it is enough to consider a semmering in this case, and then apply this theorem to the semmerings H and K in the previous one. So let us consider a semmering X and a collection of subsets of H. Take note that this is not a necessarily pairwise disjoint. However, we are saying here that I can find another collection of elements in the semmering. Now, the collection is pairwise disjoint, and 1, the union of the original collection, A sub j's, is the same with this new collection that is pairwise disjoint. And for each j from 1 up to n, I can find a set of indices S sub j corresponding to the indices of the C sub case, okay, 1 to n, such that each of the A sub j in the original collection would be the union of some of the C sub case. Here, the index is taken in this set S of j. So this is essentially what we have used in the proof of the previous theorem. We have applied this on the semmering H and also on the other semmering K on Y. Okay. So the proof here is by induction. On the number of elements of your collection. So for the basis step, you suppose or you verify that this is indeed true for n1. If n is equal to 1, then you just take m equal to 1. And you could verify immediately 1 and 2. So that's the basis step. Induction step. Well, let us suppose that 1 and 2 are valid for n sets in H. This is what we call the induction hypothesis. So what is the statement 1 and 2? So we are referring to the conclusion satisfied by the theorem. Okay. Now, so our goal is to show that it is also true for n plus 1 sets in H. So let us take n plus 1 sets in H. A sub j, j from 1 to n plus 1. We apply the induction hypothesis to the first n sets. So j from 1 to n, so that 1 and 2 are applicable. Okay. So with this, let us look at the difference. So to have an illustration, suppose that we have the sets C1, C2, C3, C4. Okay, suppose that the union has been partitioned into the sets C1, C2, C3, and C4. And in general, suppose that this is an plus 1. Okay, let us concentrate on this portion. And this is basically an plus 1 minus the union of the C sub case. k from 1 to m. Okay. So let us write it down. So an plus 1 minus the union j from 1 to n of the a sub j's. So this is the same as the one that we have written above. And why is this the case? Since this union here is the same as the union here by the induction hypothesis, and this is the first property. So going back to the statement of the theorem, this is what we are using. Okay, we have shown last time, in fact, we have used the third property of a summary and applied induction to say that I can write this as the union of the d sub l's, L from 1 up to p. And here, d sub l's, elements of the summary, and they are pairwise disjoint. So a set difference of an element in the ring with a union of elements in the ring can be written as a pairwise disjoint union of another elements of the summary. Okay. So in this illustration, I have m equals 4, and let's say p equals 3 for a simplicity. So let us divide this into 3. So this is d1, this is d2, and this is d3. So we have written the set difference as the union of pairwise disjoint elements in L. Okay, now there are two portions here. The one in A sub n and the one not in A sub n. So let us point out here. These two sets. So take a set. In this case, we took C sub 4. So the set here would be C sub 4 intersection an plus 1. And this one would be C sub 4 minus an plus 1. Okay. Now we do that for all j, or for all k. So for each k from 1 up to m, these are the indices of the C, okay? We could write the C sub k minus a n plus 1. This is basically the third property. And the index here should be n plus 1. I can write this as a pairwise disjoint union. Let us denote that by dk, let's say L. L from 1 up to p sub k. Okay. For some pairwise disjoint DKL, L from 1 up to P sub k. So the number P depends on K in general. Okay, so this means that this set difference here, which is colored in yellow, can be further divided into smaller sets. So we could divide this, and this is your typical DKL. So one portion would be DKL. Okay, now we have constructed the required collection. Indeed, we combine them. So our claim is that the collection C sub k intersection an plus 1, k from 1 to m. Okay, these are the blue regions illustrated here. Okay, let us remove this to avoid a confusion. So the blue region in this figure, okay, so those are the intersections. Next, we combine the d sub l's, L from 1 up to p. So these are the set difference, okay, of an plus 1 with the union of the c sub k's, the red region here. And then we combine the DKL, here k will run from 1 up to m, and L will run from 1 up to p sub k. We claim that this is the desired collection, satisfying 1 and 2. Okay, what is this 1 and 2 here? The conclusion of the theorem. So let's highlight those two. Now for the sets a sub j, j from 1 up to n plus 1. So that's the required collection. Okay. Well, you could see immediately here that all elements are now in H. Okay. So let us emphasize that this collection collection of elements in H. Well, the d sub l's and the dkl by construction belong to H, and the c sub k and an plus 1 are also in H. Hence, this is in H by the closure with respect to intersection for semirings. Okay, so indeed, this collection here, combining the sets that we have constructed a while ago, are elements of the semiring H. Okay, so if you want to verify, so let us verify the first one. So the union of the a sub j's, j from 1 to n plus 1. So we cut this. We just concentrate first on the first n sets, and then consider the last. Of course, you could write this as AN and then subtract the union. Okay, that's the same because we already considered the union of the n elements in this portion. Okay. Now, we have written the union of the A sub j's according to the induction hypothesis. This is the sum of the C sub k's, k from 1 to m, and I will divide this into two parts. Those that are in AN1 and those that are not in A sub n plus 1. So that's the first union. For the second one, we have by construction written this set difference as the union of the D sub L's L from 1 to P. Okay. Writing the first and the last terms as is. On the other hand, writing the second term as follows, L from 1 up to P sub k. Here we are using this equation here. So this is dkl. And the last expression is basically the union of elements in the collection of our claim. And this is precisely the sets involved in this collection here. Okay, so we have written the union of the n plus 1 sets as the union of elements in the collection of our claim. And likewise, following the same method as above, you could write this by applying the second statement of the induction hypothesis. You could write this as Sj C sub k, okay? But I will divide C sub k 1, those elements in AN plus 1, and the other, those that are not in AN plus 1. And adapting the same strategy, you will end up with the following union. So take note that this is just a sub-collection. Here, we just took the union of a sub-collection of elements in the collection of our claim. The collection is stated in our claim. And this is for all j from 1 up to n. And finally, for the last set, you could write this as the union k from 1 to m, C sub k intersection AN plus 1, and then the union of D sub L. Okay, the union of this D sub L is basically this red part here, okay? And then the first component, what is that? So we take the intersection, we took the intersection of the C sub k's, the union of the C sub k's with AN plus 1. That would be this, that would be the green region provided here. Okay, take note that in the collection, there can be empty intersections. Okay. If that would be the case, then you can retain them or ignore them because in terms of taking unions, they do not contribute to the results. Okay. So the green shaded region here corresponds to this part. Okay, so that's the intersection of the union of the C sub k's and an plus 1. And on the other hand, the union of the D sub l's, which is the set difference colored in red here. So if you combine the two, you will get an plus 1. Okay. Hence, we have also written an plus 1 as a union of a sub-collection of elements in our claim. Okay, so that ends the proof. And we have verified, indeed, the theorem that we have, or the result that we have applied previously. Okay. So let us see here. Recalling the theorem. Okay. So here is the theorem. So given a collection of semirings on X, a collection of elements on a semiring on X, we can write it as a pairwise disjoint union, and each of the set in the original collection A sub j's can be written as the union of some elements C sub k in the collection. Okay, so for the next lecture, we will consider continuity properties of premeasures.